So I'm Johnny Winn. If you haven't met me before, I'm a senior software engineer at Weedmaps. I'm the host of the Elixir Fountain podcast. No, it is not a dead podcast. In fact, we're having a panel tomorrow, live here somewhere in one of these rooms. So you're more than happy to come join us and hear from some of the keynote speakers that will be up there. Well, obviously, I'm going to create a channel in the Wahoo, I think that's how you say it, app, where you can actually post your behind the code. Is everybody familiar with behind the code questions? Is anybody familiar with Elixir Fountain? Yeah. Okay, so 5 behind the code, real quick. I'm going to give you it's 5 questions that have absolutely nothing to do with code. So you can ask anything, like, what's your favorite thing for breakfast? All sorts of stuff like that, because I find it's really important to learn a little bit about these people, because you see them as open source projects, you see them as a pull request or something like that, but they're actually real people with lives and families and sometimes kids and sometimes relatives are taken care of. So if you know a little bit more about them, the next time you go to submit that PR that says, why doesn't this thing work for me? You take into consideration that maybe they have something else going on. So anyway, so there will be questions ready for you. But today we're going to talk a little bit about evolution. How many people have ever heard of evolution? Really? I can't believe not every hand went up in this room. Has everybody heard of evolution? Yeah, wow. Can you see this is interactive here? I'm expecting something out of you. Back to the talk. I'm Johnny Winn, senior software engineer, host of Elixir Fountain. You can find me on Twitter at Johnny_Rugger. That is not my last name. That is because I played rugby for a number of years, all the way up to semi-pro, by the way. As you can tell, I'm still in game shape, but I'm planning on getting back into it. So, today, what we're going to do is we're going to talk about this experiment. I think it is very important to experiment with your code. It is important for you to learn, take on concepts that you're not familiar with, or that maybe you want to learn something new or learn how things work better than they were before. A lot of times, we get so caught up in what we're doing every day that we forget that there's other worlds out there that we can explore. Genetics being one of them. But while we're doing this experiment, we need to set some rules. You can't just go willy-nilly and just start writing code. You have to understand what those rules are going to be for the experiment that you're conducting. Then you can build your playground. Now you have access. You've set your parameters. You can define things. So then you can go ahead and you can actually work on your experiment. So you're probably all asking, why genetics? Weedmaps, no. Genetics. Oh, okay. Well, I know I'm killing the video guy back there. I'm walking all around. Hey, I'm trying to stay close to the box. I just got to be outside the box, man. So why genetics, Johnny? Well, this is some of my kids. I have more, only one more. Actually, so what this is actually a picture of my daughters with my youngest son. My oldest son is missing from this, but in his place is my granddaughter, who is in my stepdaughter's belly. She is now almost 1 year old. My wife and I look very similar. And actually, it's funny when you see the two of us together, a lot of people are like, we were just having this conversation, believe it or not, last night. It's not ironic, it just happened. Where somebody saw my daughter, one of my daughters, the youngest one in the green skirt, with my wife, and she's like, oh, you two look so much alike. And my wife is like, well, you should see her with her dad, because you're going to say, those two look a lot alike. Now, if you want to see someone else, this is my son, who absolutely loves being in photos. Can you tell? Oh, he is, man. He was happy. Well, if you go back, this was at a baby shower. As you can see, he's thrilled to be at the baby shower. But we look a lot alike. And so when you see all of us together, even my stepkids and I, we all have blue eyes. Actually, a funny story about that, my older son, when he was dating this girl in high school, we met her family and everything like that, and we were all together. And the mom looked at us and she was like, y'all are freaking me out. And we're like, why? And like, because your eyes are all so blue. I mean, it's like kind of freakish. But yeah, we all have blue eyes. We all kind of look alike, but my wife and I look alike. So obviously, as we have kids, they're going to kind of look like us. So that's kind of why I got curious about genetics, seeing what kind of experiments you can get into. Now, for those of you that are longtime code beamers, you may remember a talk that I gave a few years ago where I took it more of like pea pods reproducing via almost like pollen. The experiment was basically set up. It was similar in the case that it was organisms that were spun up under OTP processes, but they basically threw pollen or DNA out into the air, which would sync with other organisms' pollen, and then they would reproduce. But it doesn't turn out like a really cool thing to look at, really. It's just, you're just watching this DNA fly through the thing. So when LiveView came out, I was like, you know what? I think we can do something with this. So what I did was create a little world. Now, essentially, we have a petri dish here. The idea is that you put food in the petri dish, you can seed it with a certain number of organisms. These organisms are just processes. As these processes kind of do their thing, where they move around looking for food and things like that, they reproduce, they eat. If they don't eat, they die. If they run out of food, so you can have all sorts of fun. Like if you can see, I've got the max food count, which is really the seed count, is 10. So it'll throw 10 randomly in at a time on an interval. So you can sprinkle more food in if you wanted. You can sprinkle less food in, which that's kind of mean. You're like starving these processes. And you can seed it with a number of organisms. Now, these organisms are randomly generated. So we'll get into kind of some of the traits that they have, but you'll see they're like super detailed organisms. I mean, I spent a lot of time designing the way these organisms look. So if you could all just please be appreciative. We'll start by seeding with food. It takes a second to kind of get it in there. Because it's a timer, the idea is there's delays. But any second now, we'll start seeing some food pop in. There we go. I find it when I run these experiments that it's always best to throw the food in first, so that way when you go to start adding the organisms, they have something to eat. Because, I mean, what's the first thing a baby wants? Food, right? All right, so let's do, now the funny thing about population is 10 organisms doesn't sound like that much. And so as you can imagine, it wouldn't take very long for these things to all kind of be similar. So the idea is, does anybody know what the minimum population size of humans has to be able to reproduce long term? It's 200 and something. It has to be at least 200 unique people to be able to sustain a population. I'm not going to put 200 organisms in here because it's a very small screen. Now, keep in mind, we're getting ready to look at these organisms for the first time. I have spent a lot of time working on the way these look. Please be appreciative. All right, there they go. Yay, look at them. So now we've kicked off the experiment. The experiment's running. We have food in the dish. We have a population. We can actually add some more. If you notice, they're all super big variety. So let's go ahead and generate some more in there. I want to try to get maybe a little bit more. That'll throw us a nice little population. Now, as you can see, some of them are small, some of them are large, some of them are moving faster than others, and some of them are just kind of slow, kind of stumbling around. That brings us, hold on. There is a talk here, so that gives us, that brings us to our rules. What are our rules for this environment? Actually, I have to hit the slide. All right. One of the first things we have to do is we have to locate our nearest neighbor. As these organisms are moving around, they're looking for food. They're looking for other organisms to reproduce. So finding the nearest neighbor is one of the first algorithms that we have to conquer. We have to say, how are we going to get to them? We also have to know, yes, it's one thing to know where things are in the room, but it's a completely different thing to know how to get to them. So we have to actually build a mechanism for these organisms to move forward towards things that they're looking for, whether they're hungry or whether they're looking to mate. So we have to work on our trajectory algorithm. Collision detection. If you don't know how to deal with collision detection, whether you're running into a wall or looking for food, you won't know if you've ever found anything. Fitness will cover, because our fitness, is anybody familiar with fitness in regards to genetic algorithms? All right, I'm going to have you explain. No, I'm just kidding. So fitness, the idea is that as you're looking at organisms, there's going to be certain traits that are going to be more important. Our traits, we have stamina, speed, and strength. Those are the things. So at any given time, I can't remember what I set it for. We'll check it in a second. But that's the trait. So organisms are looking for other organisms that have a better fitness than they currently have. So there's a minimum fitness that they have. They're searching for organisms that are going to be either fitter so that they have a better survival rate. That's the too long didn't read of fitness. The other thing is we're going to talk about is how traits are assigned. So there's various ways that traits can be genetically passed. So we have to actually write those algorithms to be able to deal with that. So now that we kind of know some of the rules we have to follow, let's start talking about them. Here's nearest neighbor. It's actually pretty simple. You just have to run this little calculation to find out where your nearest neighbor is and get a set of coordinates to get you towards that nearest neighbor. The organism basically looks around the petri dish to find where those nearest neighbors are. And you can see this one is, I call when it's ready to mate, it's just called ready. But you can see here that it's looking for organisms in the petri dish at this point, and it's calculating the fitness based on their DNA versus the ideal fitness for the scenario. And then it's going to calculate the distance to that nearest neighbor. And then it's going to get a set of coordinates back. And those coordinates, that's what we have to find out. Because it has to actually start moving incrementally towards that item, or that object, whether or not it's food or another organism. So when we calculate the path, here's that formula broken down into code, where we actually set a series of points that are going to get us there. Now, obviously, if it's food, food is stationary in the petri dish. It doesn't move around. But other organisms are also moving around. They might be chasing food. They might be chasing other organisms. So it constantly has to, when it's in the move status, it has to continue to look and say, and recalculate that trajectory and say, okay, I am going to be moving forward towards that thing. How do I get to it? Now, the funny thing is with this, I'll admit I kind of fudged it, but you know what? It's my experiment, not yours. So once you start moving closer, as you can imagine, if every time you're looking for a set number of steps, you're going to infinitely have more steps, so you'll never actually reach there. So I kind of once you get close enough, you make a big jump. You're like, all right, I'm there. Like I said, it's my experiment, not yours. So the one that is actionable is actually this first coordinate. We know that we can move to that coordinate, and it's going to move us towards that object. Once we move towards that object, we can then look around and see if it's still the closest thing that we want to get to. Do we still want to continue moving? We recalculate that and move on to the next step. Now, obviously, if you're moving around, at some point you're going to run into things. So you have to determine how to tell whether or not that organism has run into anything. We basically have to look at the distance between the two centers with the radius included, because obviously you're going to hit the edge of something. This is mostly concerned about the walls. Obviously you can run on top of food and you're fine, you're going to eat it, but you can't get outside the petri dish. So if you can't get outside the petri dish, you need to know when you've actually hit a wall. So we have a couple things we're doing here. One is object detection, where we actually take the two objects and we figure out the distance between them. And then we take that and we figure out the radiuses and if we've actually bumped up against it. Now, wall detection is the other thing, like I mentioned. We have to know at any given time an organism has to know at any given time where it is in the petri dish to know that it's hit a wall or not. If it hits a wall, it has to bounce back and start moving back in. When we go over the actual, the application itself, when we start kind of breaking down the OTP part, you'll see that the public API for each of these modules is really small. The organism, keep in mind, is an organism. It's doing all its internals on its own. The only thing that really it has to know is if it's bounced into something. Y'all work out? Fitness. All right. Now, I'm going to tell you, I kind of fudged on this a little bit. I didn't get too complicated. Why bother? It's my experiment. Fitness is pretty simple. If the fitness is what you're looking for, all you are is looking for something that is at least what you are or better. So in the case of strength, stamina, or speed, the idea is that you're looking for something that's at least as strong, fast, or has as much stamina as you, and those are the objects you want to try to reproduce with. Obviously, to get a better gene pool. Now, it gets complicated when you start assigning traits. How many people are familiar with like how traits are assigned in genetics? I know you do, right? Yeah. Oh, come on, just go full on. They don't know. I won't tell them. He's actually my seed in the audience. I got him prepped. He's answering all my questions later. So, traits. We got to figure out what those traits are. Did I lose my clicker? Oh. Okay, there we go. All right. Here's some basics about traits and how they're assigned. We started with that first generation. Within that generation, I've kind of broken this down. I hope it's easy to understand. So we have color, which color is divided up into 3 numbers, up to 255. That way we can set it nice and easy. Strength is up to 255. Speed and stamina, the same thing. So obviously, we're not single reproducing. We're not splitting these organisms. So really, replication isn't what we would typically do. Single-celled organisms generally do the replication, where you're just basically mimicking one and the other. You still have mutation as part of that process because that is a possibility. But for the most part, they just kind of split, and it's the same two cells moving forward. That doesn't do us any good in this scenario. Now, the ones that we do use are crossover and mutation. Crossover being where you have two that mate together, they take their DNA, they might take one from some and one from the other, or split it up. So as you see in generation 2, let's get to this one. This first organism, pretty much the next generation was pretty much the same, but it did take from the other. Kind of simplified. Honestly, the code does it a lot more complicated, but I didn't want to confuse with all the different ways. We'll get into that. The other way is the mutation. So now with mutation, and I did 0. Typically, the mutation wouldn't be a 0, but I wanted to have something that would call out to this is really odd. It's when 2 organisms, they reproduce. Yeah, there's some crossover, but there might be a mutation that springs up, which would change a value. So here's actually what that is in code. What I do is I actually take the 2 DNA from the parents. For the kind of crossover, like a little bit of this, a little bit of that, there's the average. So something like speed, one speed, another speed, there's an average that can be calculated in. I actually add that to the probability twice to give it kind of a little bit more of a chance. Mutation is in there once. So it's really rare, possibly, that a mutation happens. I try to prevent a whole lot of mutations in the population. But then I do this kind of crazy map-reduce thing where I take the parents and I can increase the probability that they'll match, or I can decrease it by changing the number of times that they're added to the set. So ideally, what a random value is pulled from each one of those. So you could have a parent's trait, or you could have an average of the 2 parents' traits, or you could have a mutation, which might be a value that isn't related to either one. That's basically how we determine what each characteristic is. Now, in the actual in the reproduction process, each one of those is singly called out. So, like for color, there's 3 values. This is called 3 times, so it could vary even within the color choice. Obviously, DNA is really complicated, so you have all sorts of little variations and little tweaks, just like when you can think about colors, might not necessarily show up on the screen, but there is a variation there. So, there's our traits. Oh, that's right, we should probably check on these things. So, let's take a second to observe how wonderful my GUI skills are. Yeah, so it looks like what's happened, and I've seen this before. So the funny thing about this experiment, this is almost like live coding or like working with kids on stage. You really never know what you're going to get. This runs, sometimes it runs perfect, and you get like a nice diverse population. Sometimes you run it and you get this. Actually, I gave this talk at a big Elixir in New Orleans back in November, and I had run this simulator so many times, I was like, man, this is perfect. I get this like great, like diverse population, and it's gonna be awesome. I got up and I ran it on the talk, and then we're going through. The entire thing was blue. I was like, oh, really? So anyway, let's see here. I guess now that we've kind of talked through some of the rules that we've set in place, we haven't really touched OTP yet. So we kind of want to know how this stuff is all working within this Petri dish. Now, here's a nice simplified version of everything. Essentially, you have your application that's running, it's storing a Petri dish. The Petri dish is the central container for all these organisms and food. And then you have a food generator, which is just a process that periodically dumps food based on the interval you told it that it should be able to dump food in. The food supervisor kind of monitors those processes. So if there's something that goes wrong, the food can be put back. But in all likelihood, it's either eaten or it deteriorates. It actually, over time, and that's basically a random. So something might be food for 10 seconds, and something might expire at a certain time. Obviously, that's the way the really real world works, right? So there's no preservatives, no additives. It's all straightforward. We also have the organism generator, which is responsible for spinning these up, and of course the organism supervisor. Now, all these processes can die or go away. Like food can be eaten and that process just quietly goes away. Food can deteriorate, quietly go away. An organism, if it does not continue to feed, will die. So let's start with the Petri dish. We talked a little bit about the APIs. Now, I'm really big when you're setting up your modules. People say API, and the first thing that they think about is, oh, my web API. That's not the first thing you should think about. It's how you actually interact. How does something else interact with your code? In our case, for the Petri dish, we have a really simple API. It can give you a list of all the items in the Petri dish. That really comes in handy when something's looking around the Petri dish. It needs to know what's there. And it can draw to the Petri dish, which is really the draw is just refreshing where everything's at currently. And obviously remove things from the Petri dish when they die, they're eaten, or they expire. The food generator has a pretty simple API. Begin generation, starts up, starts throwing food in there. As you can see, it was really time sensitive. We can change the frequency, we can change the bounds, basically like where the food populates. One of the things that I thought was that when you're throwing food in the dish, maybe you want to try to put it in a certain area of the dish and then start the organisms in another area and see if they all migrate to it. Thought it was kind of fun. You can also change the delay. So like when your food goes in, if you notice that even once I hit generate food, there was kind of a little bit of a delay. Well, you can actually change that delay. So if you want food to just pop in right away, or if you want every time, add new food, go ahead. And then of course the max count. Now, food, it only knows if it's been consumed. That's pretty much it. The timer will expire if it expires, and then the food goes away. Now, for the organisms, it's a little bit different, but the organism generator basically, it's similar processes where you're basically changing some of those same sort of things. Like you can delay, if you notice that when I put the organisms in, there was kind of a delay as to where they popped in and out, or they popped in. So you can change all those kind of things. But for an organism itself, the public function is a bounce. Basically, when it runs into a wall, it gets a signal that it's been bounced, and it turns around and goes the other way. It's a fun little story about this when you're working with like collision detection and bouncing and things like that. I would have these organisms that would just keep hitting the wall, and I'm like, man, these things are dumb. So I made them a little smarter. Like they realize if they hit a wall that they probably shouldn't go that way for a little while, and they'll start going the other way. But then, of course, you run into the thing where they start getting out, and they're like, oh, hey, I can go back to that wall. Stupid organisms. So I haven't talked about LiveView yet. It's kind of funny, a whole talk on LiveView, and I haven't even mentioned it. Well, I kind of mentioned it. This is pretty much it. LiveView is not super complicated. A lot of what LiveView is doing has like nothing to do with your Elixir code. It's basically serving HTML back up. Is it because I'm moving around too much? It's up to you. Oh, sorry. Told you. Shake, rattle, and roll. I'm going to stand very still and try to talk about this. This is it. It's really you just mount. You mount in your LiveView process, and then you can actually send signals to it. With the Petri dish doesn't need to really do anything. It just needs to kind of refresh the UI as things move around. So it actually calls itself, you see up at the top, the timer send interval. Every 100th of a second, it sends a signal to itself to say, hey, by the way, you should probably grab whatever's in the dish. In the meantime, the other processes are constantly pushing to it and saying, hey, I'm here, I'm here, I'm here, or I'm not here anymore because I died. All right. I'm really nervous here. I feel like I'm about to, they're just clustering. They tend to cluster, especially once they kind of get in this little thing where the food is spawning probably underneath them. And so the food is there. They don't need to really move around anymore. And there's plenty of mates because they're right there. And probably their fitness is now all kind of about the same. And so that's why we get like all the same color. Because now, remember we set to like 10 times each of the parents will be in there. Well, if the parents start looking alike, and that's most likely what the selection process will be, eventually everything's going to look alike. Now, I could probably put 200 in here and we could have a nice diverse population, but that's a time for another talk. Oh, wait, hold on. I can't click the button on this screen. Now, that was the one last time to look at it. Every time I run this simulator, it's different. And I can tweak little things with the simulators to have different outcomes. I can change fitnesses on things. I can change how organisms come in. I can change how food is produced. So all these things kind of matter in the environment. So the little experiments kind of come through in like little tweaks. Sometimes it looks really cool, and sometimes you have a big blob of color that you can't tell anything about. Before I get to that slide, part of the reason why this is in the frameworks talk is if you notice that the transition we kind of went through with this, we started with the functions that we needed to make things happen. It had nothing to do with LiveView. It had nothing to do with OTP. So often we get kind of bogged down with, I'm in this framework. I've got to, let me think about how the processes are going to work. Don't start there necessarily. Now, obviously, if you're building something that's known, you start with what you need and you can build it out. But when you're thinking about these experiments especially, start with the functions. See where the functions take you. Make sure you've kind of got some rules set up for your experiment. Make sure you're doing what you need to do from a function standpoint and analyzing that part of the data before you worry about the framework. Because you can always swap in a framework. I've seen a lot of times people come in, and this is what I do want to get to the framework part, is when you bring the framework in, at that point, respect the framework. Use the idioms of that framework. Work with OTP the way OTP is meant to be worked with. Don't try to roll your own thing and be like, oh, I'm using OTP. And it was like, you're not communicating. Part of the beauty of using a framework is communicating your thoughts and ideas to other people without having to be in the same room with them. If I say, I'm using OTP in my project, I have a supervisor running processes, everybody in this room should know what I'm doing. If I say I'm using OTP, yeah, I figured out this way to do this crazy thing. It's like, okay, well now you've lost that communication channel that you had. The same goes with Phoenix or any framework that you're using. If you stick to the idioms of the language or the framework, it makes it easier to communicate those ideas to others. Now, as far as the experimenting part goes, I'm a big advocate for experimentation. Like I said in the beginning of the talk, find something cool idea that you want to work with, something that you want to explore that has absolutely nothing to do with work, and then go explore it. See what you can do, see what you can build, because that's when your mind really starts to kind of open to the things that you do every day. It changes the way you kind of think about things. I did take out a slide on this one. So the first time I gave this talk, it was kind of a funny story. It's sad. I don't want to end on a sad note, so I want everybody to know that like this actually turned out really well. I gave it the last talk at a conference on a Friday afternoon. I get a call from my daughter, one of my daughters that you saw in the beginning, and she was like, "I really need to talk to you. Give me a call when you get a chance." It's like, okay. Keep in mind, I haven't been back to Florida in a long time. We're from Florida originally. I'm in New Orleans. I was like, all right, I'll give her a call. You know, of course, I'm working on my talk. I got to a point I was like, all right, I'm ready to call. I called. She's kind of crying. She goes, "I wanted to let you know that your grandfather died." So I was like, oh, man, that sucks. I was really close to my grandfather growing up. I hadn't been back as much over the last few years as things happen. But I also know that, like, he was really cool about letting you go learn on your own. Like, yeah, he would kind of coach you and give you parameters and, like, you know, make sure you kind of stayed in line. And trust me, with me, that was probably more difficult than most kids. But he would always let you experiment, and he always figured that you're going to figure it out. And so I dedicated this talk originally to him. I did take out the slide, and I debated on whether I was going to mention it, but I do want to mention it that I did dedicate this to them. You know, my family and how I was raised growing up has a lot to do with how I am now, and a lot of the freedom that they gave me then allowed me to do what I do now. So thank you for listening to me. I appreciate it. All right, here's the deal. How much time do we have? Okay. All right, well, we have as much time as we want, so feel free to ask me any question that you want. You can even ask me behind the code questions if you want. So, anybody? Yeah. Mm-hmm. Well, there's still parameters that they can only get so fast. And so, and depending on, yeah, I mean, technically they can get us all really super fast, but there's still a peak. They can't ever go over a certain threshold. It's kind of like a human. There's only so fast a human can go, so you're always going to hit that boundary. So
is there a prioritization between organisms looking for food or for a mate?
So there is. So I did set some boundaries around minimum stamina. So if they get hungry, if they hit a point, they don't care about reproducing. They're looking only for food. And then once their minimum stamina is met, and of course, obviously when they eat, it jumps up. There's another timer that's running for their reproduction. So there's like, at some point they're like, okay, I'm not hungry, but I'm now hitting a threshold of a minimum that I need to go reproduce. And so then it's like a one-track mind. They're just going to reproduce. And so the cycle kind of goes back and forth. There is a possibility, sometimes they just kind of move around because depending on, all those times are random. So some organisms need to reproduce really quickly, but they have a really low stamina too, so that they're constantly worried about is reproducing, and they don't even think that they need to eat. And so they'll die off. Yeah, they might reproduce, but it's like, kind of, yes, I guess. But so you do run into, and that's the fun thing about this is, and the code is up on GitHub. The fun thing about this is to play with is to kind of start tweaking things and moving numbers around and kind of see, you know, and honestly, it's an experiment, it's a playground. I would invite anybody to pull it down and play with it and tell me, hey, why didn't you do this, that, or the other? And then I say, well, why don't you do this, that, or the other and see what it comes out as. So, you know, I mean, but that's the thing is you can move all these numbers around. So, mm-hmm.
So, like, speed, stamina, and strength are all, I guess, like, higher is better. Did you do anything different with color, or was it just?
No, and I thought the color is more, I thought about working that in, but at the same time, it's like I didn't want to overly complicate. I mean, color gets kind of really, it's harder because there's 3 values for each one. And so then it's like, okay, well, how do you say that this color is big? Because you've got such a range that you can't say, okay, well, this color is better than this, like this fitness is better than that one, where speed and stamina, and those are easy. All right, you called me out. I took a shortcut. So, but hey, the other thing is I'm not a geneticist. I am staying at a Holiday Inn tonight, so maybe tomorrow I'll have those answers for you. So, yes, sir.
I really like the part where you talked about just dealing in functions and looking at it from the API standpoint.
Mm-hmm.
OTP specifically, or Phoenix,
No, they're actually, there's modules with just rules and even like just behaviors and things like that. And so the OTP part is really small and calls into those things. And so that you can actually move those around if, add a different type of organism process. Funny side note, I didn't know if it was too soon, but I was thinking about releasing a virus that would actually go and try to kill organisms, but I didn't know, and they didn't have enough hand sanitizer to put it in the back of the room, so too soon. Anybody else? Yeah.
So the whole thing with like organisms with their attributes feels like a kind of like classic example object-oriented type problem where each of these is an object. Like did you find that like doing this with a functional approach made that easier, harder, just the same?
So I try not to get too caught up in that sort of thing. There's the old thing that, Erlang is the most object-oriented language out there because it's all about message passing. Obviously, at some point, you have to define a data structure. That data structure looks an awful lot like a class or an object in an object-oriented language. There's an organism module that defines what an organism is. But then the process for those organisms, those are processes that once they're seeded with that, it's almost like seeding with that data structure, and then the timers are all running to say, okay, I need to do this, I need to die, I need to eat, I need to mate, this thing, this, that, and the other. So the processes themselves, obviously the data structures are structured to define those things. You have functions that are executed to calculate a behavior or do whatever it needs to do for that. The processes themselves are just managing those life cycle processes. So it's almost just kind of going, taking the loops. That's why I said like bounce is the only thing. You don't really interact with the organism as a process. It does its thing and it interacts with the world. So.
How are you drawing organisms?
I told you that like I'm really good at front end development. They're just divs that I've got some CSS that made them round and different colors. And,
Would the calculations tied to the same
with the calculus.
loop?
Yeah.
And so were the calculations for like
So the redraw actually, the loop for the redraw, all it's doing is the Petri dish exists as a process that's just maintaining state. That's the only thing the Petri dish does. The redraw is just asking the Petri dish, what is your state now? What is your state now? What is your state now? And then displaying it out. The organisms themselves, as they're moving around, they're looking around the Petri dish and they're moving towards things based on what their current status is. And when they move, they basically broadcast back to the Petri dish to say, here's my new location. And then the loop process is just saying, what do you look like now? What do you look like now? What do you look like now? Over and over again. Right, yeah. And sometimes that was one of the things I was playing around with. I have a feeling I'm getting kicked out here soon. I'm not sure. Y'all good? 4 minutes? Shh, I got 4 minutes. I'm gonna talk real slow. No. What was I saying? So the redraw, yes, it's just asking. Depending on how your timers are, so like slower moving organisms look more jumpy sometimes or faster ones, I should say, because they're moving faster. And so they're actually moving faster at a faster rate than the refresh on the live view. So I had to you start massaging the numbers a little bit to kind of like, okay, how do I make this look as fluid as possible? It's funny when they start mating and reproducing and things like that, and sometimes they get slower. Like if speed isn't one of the fitness, then they don't really care about fitness. And they start getting really slow, but then they're really hungry because stamina might be what they're looking for, is to be, And so, yeah, you get really slow moving objects that are just kind of like looking for food, but they're not fast enough to get to it because something else is getting to it first. Huh? What? Yeah, like teenagers, yeah. It's a global setting in this case. So the idea was to set the Petri dish, like the organisms are all looking for the same thing. You could have individual ones, And technically speaking, each individual organism could have their own. It's part of their DNA is what the fitness is. But for the Petri dish, I say that this is what the ideal fitness is. So some might be looking for a fitness that isn't necessarily the ideal fitness for the Petri dish. So. All right, everybody. Thank you.